Hi, everyone. Thank you so much for attending this session. I'm going to go ahead and get started. I'm pleased to be here. The last time we had a seminar from this series was fall of 2019, and we've been trying to kick it back off again, and it took 2.5 years to get the activation energy. So today I'm going to be giving a not so mathematical introduction to p-values and multiple comparisons. And before we get going, I just kind of have a confession to make, which is I super do not love this topic. But it's a topic that we all sort of have to deal with, and therefore it's a topic that I get asked about the most. So what we're going to do is talk about some of those controversies, acknowledge them, but try to tackle them in a way that's very objective, because they are the shared experience, whether you're a research producer or someone who's more of a, what I would call research consumer, and you want to be more savvy about that, you're going to encounter this topic. So we're going to focus on being objective and trying to understand where the controversies come from and help to define our terms better so that we can be more savvy, whether we're producing literature in this area or being a more savvy consumer of it. So brief outline, I'm going to give a definition of p-values, what I consider my 3 pro tips. Those are going to be more from a pragmatic perspective, an introduction to the source of some of the debates surrounding multiple comparisons, general approaches that you're likely to encounter in the literature, 3 pro tips, some resources, and if you have the seat stamina to stick it out, we have a bonus pro tip at the end. So first is a definition. And if you've taken a stat class, you've probably seen this defined before. I'm going to go about it in more of an intuitive way. So first you start off with something that we refer to as our null hypothesis. And you could think of a null hypothesis as being sort of a default position. And pragmatically, it's usually framed as no difference between something or no association of something. So an example would be no difference in stroke risk between the new drug and a placebo, or no difference in gene expression between cases and controls. So we're assuming by default that that's the state of the world. Then you do your experiment, you collect some data, and you perform your statistical analysis. And typically an analysis involves computing a p-value. What a lot of people misconstrue about a p-value is the definition of it. It's basically the probability of observing a set of data given the assumption of that default position. So as a schematic, imagine that you're computing your p-value. Then you could think about what is the distribution of your data if that null hypothesis or default position is true. So we would expect to observe something where this blue line is. If that default position is true, we would expect there to be no difference. And so what we're trying to see is what is the probability of observing data that is further away from our default position than what we actually observed in our experiment. So the data that we observed in our experiment, we're putting that where this purple line is, and the probability of getting data that's further away from the null than what we observed is indicated by this blue shaded area right here. And so the thinking is that if that blue shaded area is small, then what we observed is not very compatible with that default position of the null hypothesis, and the data that we observed, and anything more extreme than that, is unlikely if the null is true. If this blue shaded area is large, then what we observed isn't maybe that incompatible with that default null hypothesis position. And so what we observed, and anything more extreme than that, is maybe not that unlikely if the null is true. Now, something to be aware of with p-values is that contrary to the way they're conveyed in some of the published literature, it's a continuum. It's a probability, so it ranges from 0 to 1. The idea here, again, just to reiterate, is the less compatibility you have with the less compatible the data are with your null hypothesis means the more rare or unlikely it is to have observed the data that you observed, and that leads to a smaller p-value. Commonly, this is carried out or computed in what we call a two-sided way. Notice in the schematic, we have the blue shaded area on both sides, even though what we observed is actually at this purple line here. So what you often see in the literature is that a p-value is compared to some sort of threshold value to define statistical significance. And the most common value for that threshold is 0.05. But make no mistake, at its core, a p-value, it's a probability, it's on a continuum, it ranges between 0 and 1. So again, to be more formal, and whenever I teach a statistics class, I always put this question on the test to make sure people know how to define these things, is that the p-values are the probability of obtaining data as or more extreme than what was observed, assuming that the null hypothesis is true. The often misconception of these, or the often misinterpretation, bear in mind that p-values are not the probability that the null hypothesis is true. So you're not making an assumption about the probability of the state of the world. What you're doing is talking about the probability of data given an assumed state of the world, where that assumed state of the world is that null hypothesis, that default position. So making sure that we're aware of what the definition of the p-value is, this leads to some pro tips. So pro tip number 1 is when you're producing results, report the full result. So on the left-hand side, we see a table, and I've seen tables that look like this in literature, where it's really just sort of a checklist of which p-values are less than 0.05 or not. On the right hand, we have a richer set of results. Here we're just comparing 2 drugs to what I guess would be a placebo, the yellow drug. And here, in addition to whether or not the p-value is less than some threshold or not, oh, and I forgot to define the term here, this NS usually means not significant. Not only do we have whether or not our p-value is less than 0.05, we have what our p-value actually was, acknowledging that p-values are on a continuum between 0 and 1. So let's report what that value is. But also it's difficult to interpret p-values without other information. So that other information would be in a measure of association. In this case, it would be like a mean difference of whatever your outcome is comparing these 2 drugs, and a 95% confidence interval, which is a way of reporting sort of a margin of error in that mean difference, and acknowledges that there is some sampling error going on in your data. The reason why we want to do this is let's compare these results. These results are both consistent with what we saw on that left-hand table in the previous slide, in the sense that that first line, the p-value is less than 0.05. The second line, the p-value is greater than 0.05. But intuitively, these are very different results. Having a p-value of 0.003 is not the same thing as a p-value of 0.043. A p-value of 0.92, which basically is indicating that you saw findings very close to the null, or what you would expect if the null was true, is not the same as a p-value of 0.1, which would be, maybe not meeting a threshold of statistical significance, but still rather unlikely. And to reiterate this some more, and to bring it back to an omics example, sometimes we have high throughput experiments, and it may be daunting to think about, well, how am I going to report the full results when I'm testing hundreds, if not thousands, of genes, sequences, texts, or whatever? So the solution there is to leverage the fact that a lot of journals allow you to report supplemental information, and a lot of the checklists, like the new storms checklist or the microbiome, that's one of the items on there, is to report full results in your appendix. So what you could do is in your main text, put a figure like what we have here on the left, where this is called a volcano plot, where on your x-axis, you have your measure of association. In this case, we have something called a beta coefficient, which you would get if you were to do like a linear regression, for example. And on the y-axis, you would have a transformation of your p-value such that small p-values have large values of this transformation, and large p-values have small values of this transformation. So this is a way of efficiently presenting some results and allowing you to look for patterns, but it's not your full result. Your full result can be shown in something like a comma-separated value file, where you would have every single taxon, gene, sequence, or whatever you're testing, your full result, and your p-value sorted by significance, for example. And this allows reproducibility and transparency about what you did. The second pro tip is that you're allowed to report all values of p-values. Any of these could be labeled, discussed, or contextualized. So going back to this example where I had my volcano plot, this horizontal line right here is the threshold for that p-value of 0.05. Notice that I labeled some taxa that had p-values greater than 0.05, and the most amazing thing happened. I did not burst into flames. I was allowed to do that. And so the idea here is that what I did is I said, okay, let me label the top 10 or 15 most significant and see if any patterns emerged. And this allowed me to view that a lot of the significant taxa came from the same phylum. I would not have been able to observe that pattern quite as clearly. I wasn't looking at maybe my top 10 or 15 instead of just labeling the top 2 or 3. Another example of this is more of a toy example related to the microbiome. And so let's say you're testing a variety of taxa and you're augmenting that taxon information with the function of the taxa. In addition to that, you have your measure of association. A common one that we see microbiome research or transcriptomics is the log fold change. And we have our p-value. All these are sorted from most to least significant. So if I was being very dogmatic about that 0.05 threshold, then what I would do is something over on the left, which is to report something like, well, only taxon X differed between cases and controls, and an intervention to increase taxon abundance is needed. In other words, I would just have my blinders on, focusing on that one related to that one significant taxon. Whereas if we allow ourselves to look at all of our results, irrespective of whether or not it passes some sort of threshold, that would allow us to better see patterns. Specifically in this case, noting that, well, the 3 most significant taxa all have the same function. Sure, those second or third ones don't reach the threshold of 0.05, but it's still noteworthy that they all have the same function. So we could say something like, well, the top 3 most significant taxa were butyrate producers that all had lower abundance in cases than controls. So not only their function, but looking at their measure of association and looking at the fact that they are all going in the same direction. And then in the discussion, we could say something like, well, a replication study and laboratory experiments, should be done to validate these findings. So we're not saying that things are statistically significant when they're not. We don't want to move our goalposts necessarily, but you're allowed to discuss them and contextualize the results. So another pro tip is to note that just because you have a p-value that's greater than 0.05, that's not the same as no difference. So here's another toy example. So let's say we have 3 prior publications and we have a current study. Let's say in publication 1, we have a p-value of 0.04. And to bring us back to something related to the microbiome, let's say we're looking at differential abundance, comparing cases and controls, and we see we have a positive value there. Let's say there's another publication, their p-value is 0.001. They also have a positive differential abundance. Publication 3, p-value of 0.03, also a positive differential abundance. But when we carry out our study, our p-value is 0.06, although we still have a positive differential abundance. And not only that, the largest differential abundance of all the 4 studies shown here. So what we don't want to do is the thing on the left and say, we found no difference in abundance of taxon X between cases and controls, contradicting previous research. What we would want to say is something more like on the right, where we say, consistent with previous research, cases had higher abundance of taxon X than controls. However, findings may be due to chance. Again, we don't want to overinterpret our findings, but we do want to allow ourselves to contextualize and not just draw that hard line at 0.05 and recognize that we are seeing a similar pattern here. So there actually are cartoons that make statistical jokes. I'm a huge fan if you've ever read XKCD. And here's sort of a tongue-in-cheek interpretation of different p-values, ranging from highly significant to, oh, we better redo our calculations. On the edge, highly suggestive, and look at this interesting subgroup analysis. And unfortunately, the reason why it's funny is because there is a kernel of truth in terms of how people tend to react to certain levels of p-values. So now that we've looked at the definition of p-values and some helpful pro tips, now we're going to talk about maybe my least favorite aspect of this topic, which is the multiple comparisons debate. So first, we're just going to step back and try to understand it. And no one can explain it better than XKCD. So in this example, there's a hypothesis that jelly beans cause acne and a call for scientists to investigate, but they're all playing Minecraft, which means they probably understand what my son is talking about more than I do. They do their study and they found no link between jelly beans and acne. Of course, all they're showing is that their p-value is greater than 0.05. But then they say, oh, well, maybe it's only in certain colors. So they call the scientists who are still busy playing Minecraft. And what they did is they repeated the study, but they tested 20 different colors of jelly beans. And they found p-values greater than 0.05, except for when they look at green jelly beans. And there's a very deliberate reason why they chose 20 different colors, because what's 1 out of 20? 5%, right? So this is exactly what you would expect to see if you carry out 20 tests. So the joke is that since they found that one significant finding at a threshold of 0.05, then it becomes headline news, front page news. And so this is a tongue-in-cheek example of what folks are concerned about when they talk about the multiple comparisons problem. But there has been a long debate going back decades about this. Some of the articles are shown right here, and this is only a subset. And what's interesting to point out is, first it starts with, these simple declarative statements of, well, you never need to adjust for it at all, to asking the question of, well, do you need to adjust it, to maybe a more nuanced discussion of why are we even having this debate in the first place. So this one on the bottom left is one of my favorites because it's getting at this notion that, what the real concern about is what is the bigger error to make that we're most worried about. And they reframed it as looking at context and costs rather than, what is the underlying math behind it. Interestingly, and this is over a quarter of a century old, but still relevant, in the mid to late 90s, there was a lot of back and forth debate going on in the American Journal of Epidemiology. So it started in 95 with the first article, and it finished in 98 when the editor at the time, Steve Goodman, wrote an editorial about it. And I always had this vision in my head of the editor basically sitting back with his popcorn, watching people duke out this debate. And so the first few articles, showed all the mathematical derivations, demonstrating the relevance of both of their sides. And what he came down to was saying, okay, we see your math. Your math is correct. The debate is not the math. The debate has more to do with the questioning scientists' honesty and intentions when they're carrying out their analysis. So he framed it as more of a human element issue that's driving this debate as opposed to a mathematical or statistical philosophy debate. So I think one unstated assumption that shows up in this debate, and I rarely see it explicated, is what exactly is your hypothesis? And so we can think about it, to keep things simple, in two different ways. One is that you're really interested in one global omnibus hypothesis. So an example from genetics would be a null hypothesis that says genes are unrelated to your phenotype of interest. And so oftentimes what folks will do is they'll test 1,000 genes. So then the concern is, well, if you're testing 1,000 genes, you're basically giving yourself multiple shots to hit your target. That's where the multiplicity concerns come in. Whereas another way to frame it is to say, I'm not interested in one global omnibus hypothesis. What I'm actually testing are multiple hypotheses. So in that case, it's not just one null hypothesis. If you're testing 1,000 genes, you have 1,000 null hypotheses. So one null hypothesis is that gene 1 is unrelated to your phenotype. Your second one may be that gene 2 is unrelated to your phenotype, so on and so forth. So in this way, the thinking is that, well, if I'm testing 1,000 genes, I'm not giving myself 1,000 tries to hit my target. I have 1,000 different targets, and I get one shot at each. So if we were to look at this visually, the concern is that over on the left, if you have your one global hypothesis, that there's concern that you're giving yourself multiple shots, these arrows representing the test, to hit your one target, which is the analogy for the hypothesis. Whereas over here on the right, the issue is saying, well, if I'm testing gene 1 over here, represented by the first target, why should that impact my findings or how I report the results when I'm testing gene 2 right here in the middle? Why would that matter? Why would the findings in one impact the other? And so, as you can imagine, if the folks who tend to frame it as one global omnibus hypothesis for one family of tests, they're often proponents of correcting for multiple comparisons. The folks who frame it more as multiple hypotheses, they're generally against the correction for multiple hypotheses or the correction for multiple comparisons. And so the easy answer, if I was looking at this from just a pure stat theory perspective, would be to say, well, if you're interested in one global omnibus hypothesis, just do your one global omnibus test, something like an ANOVA related test or ANOVA-like method. Whereas if you're interested in these multiple hypotheses, then do your multiple comparisons, but just frame it as one test for one hypothesis and be done with it. But somehow that doesn't sound satisfactory. And it's because if you write up just that one global omnibus result and then go right into your discussion section, it just sort of feels like something's missing because those results on their own just don't seem actionable. Which lends me to think that maybe the real hypothesis is more like these multiple hypotheses. But this brings us back to what Steve Goodman said as an editor in the American Journal of Epidemiology. There's concern about what are the real intentions of the investigator. Are you really interested in framing these as multiple hypotheses, or are you just trying to leverage the multiple hypotheses because the more you do, the more likely you are to find something that's, quote, statistically significant? So again, brings us back to that human element. So before we get to the pro tips, I'm just going to review briefly some general approaches that you're likely to find in the literature. So these general approaches have been developed because there's concern about whether p-values are maybe too small, too large. Is there any way that we can get them just right? And as you can see from the debate that we just had, there is a lot of disagreement about where to calibrate that. So in general, folks are worried about p-values being too large when they use this first approach, which is the Bonferroni correction. And the reason why is because it tends to overcorrect, even if you're a proponent of multiple comparisons corrections. There are also Bonferroni-like methods, but that is a long laundry list. And the reason why folks like it is that it's relatively straightforward to perform. So the idea here is that you would compute your individual p-values as usual. We call these our raw p-values. Count the number of tests you perform. We're going to indicate that as m. And you just multiply your raw p-value by m to get your Bonferroni corrected p-value. So then if you have a threshold, which is often denoted as alpha, and those of you who took a stat class would recognize this as your type 1 error, then you would compare your corrected p-value to alpha. Similarly, you could compare your raw p-values to alpha divided by m. So both of those will give you the same results in terms of whether it's below or above your threshold. So why are we saying that there's the concern that this is too large, even among proponents of multiple comparisons? Well, it tends to be on the conservative side. And I think this is the only equation I have in here, so bear with me. But as an example, let's say we're testing 1,000 independent RNA sequences where the null just happens to be true for all 1,000 of these. And we set our threshold for type 1 error is 0.05. then just due to chance, we would expect that 50 sequences would have p-values less than 0.05. And also we would expect that the probability of having at least one sequence with a p-value of less than 0.05 is basically 1. Whereas if we were to reset our threshold at alpha divided by m, then the probability of at least one sequence with a p-value less than that adjusted threshold would be 0.0488. So the idea here is that this is less than 0.05. So there's like an overcorrection when we carry out the Bonferroni. What we want this to be is 0.05, but it's slightly less than 0.05. So it tends to be on the conservative side. And for my colleagues who do omics research, their concern is, well, I'm doing a discovery study. I don't want to be so stringent with my adjustment that I can't discover anything. And what's notable here is that it tends to be on the conservative side, even in the best case scenario where all your tests are independent. What if your tests are not independent? And so this is a deliberately silly example, but it's designed to make a point. Let's say that our goal here is to carry out a study to see if arm length relates to maternal height. And so let's say we carry out one test, which is to see how the length of your left arm relates to maternal height. We have our beta coefficient, our p-value. But we want to test the right arm also, just to be sure. So we're doing our second test, which is to look at the association between your right arm length and your maternal height. And shocker, your coefficient tends to be exactly the same. Your raw p-value is exactly the same. But if you correct it, you go above that 0.05 threshold. So should you adjust or not, or why are we seeing this? The issue here is that your left arm and your right arm are so highly correlated that even though you're going through the motions of carrying out two tests, you're effectively just doing one test because of the correlation between your left arm and your right arm. And so Bonferroni treats these tests as independent. So you're overcorrecting even further if you're dealing with dependent or correlated tests. So in this case, it's overly conservative. In the case of an omics example, oftentimes sequences and variants are in linkage disequilibrium. So there's concern that a Bonferroni correction would be unnecessarily overly conservative in that situation as well. The second approach is even easier than the Bonferroni approach, and that's what I call the do nothing approach. Don't carry out a correction at all. However, the concerns and the folks who disagree with this are concerned that the p-values are too small. However, before you laugh at the do nothing approach, it's important to note that this is probably the most common approach in clinical journals, particularly randomized controlled trials. Other examples, hypothesis-driven research, and as mentioned, randomized trials. So what they do, and it's not that they're not concerned about multiple comparisons, but instead of correcting the p-values for multiple comparisons, what they advise is that you pre-specify a primary outcome and analysis. And in the case of randomized trials, they want you to pre-register your analysis plan before you carry out your study so that you can firmly plant your goalposts and not move them after the fact if you don't like your results. Now, in an omics example, this may also be appropriate in the cases of a small number of tests, like a candidate gene or candidate sequence of interest, as is commonly done in pharmacogenetic or pharmacogenomic studies. Also, sometimes we're interested in microbiome research, just looking at a small number of microbial community types as well. But again, why perhaps is this too small? Again, it's that discovery omics concern that on the one hand, it doesn't narrow the field enough necessarily to help prioritize research allocation or help you figure out what to do next. However, it's important to note that no one says that you have to set your alpha at 0.05. You can set your alpha much smaller. And so it's common in the GWAS community to have their standard alpha be 5 times 10 to the negative 8. And so instead of doing a multiple comparisons, they just at the outset just set a smaller alpha and don't adjust. So the third approach, which tends to be very common in omics research, And the reason why folks think maybe this is just right, although not everyone agrees with that, is that it tends to be more conservative than doing nothing, but not as conservative as Bonferroni corrections. But I think what folks don't realize is that they're setting their threshold using a completely different kind of metric. And they're controlling something very different than what you're controlling when you're looking at p-values. So it's important to note that there have been modifications made to Bonferroni corrections that can be seen as false discovery rate type precursors. One that does address this effective number of tests, so you don't have that silly left arm, right arm issue that we had in other precursors as well. So if you're reading the literature and you see someone using false discovery rate based methods, you may wonder, what exactly that is if you're not familiar with it. So here's some intuition. The idea here is that if you have our M tests, so that's the number of tests, whether it's genes, sequences, proteins, taxa, what we would expect if the null hypothesis is true for all these tests, we would expect a distribution that looks like what we have here on the left, which is a uniform distribution. Our x-axis are values of p-values, and our y-axis is the number of tests that are being performed. And so the idea here is that you're performing a lot of tests such that if you plot them this way, you actually can get a good visualization of what their histogram looks like. And you can see that it looks approximately uniform if the null is true. However, if some of them, if there's a fraction where the null hypothesis is not true, we would expect our histogram or our distribution to look more like what we have here on the right. And the idea here is that it looks almost like there's two distributions happening. On the one hand, we have something that looks like a uniform distribution, but with this spike of small p-values on top of it. Once again, the x-axis are the p-values and the y-axis is the frequency. And so the idea here is to say, okay, we want to come up with an estimate of the frequency of null tests. And so we want to find a line where we want to say a test is positive or a test is significant. And the idea here is that there's this uniform distribution of null findings or of null results with a small fraction of true positives. And so the definition of the false discovery rate is it's the number of false positives. So where you draw that blue line will control that divided by all positives, which again is where you would draw that blue line. And so the question is, well, how do you draw, where do you put that blue line in such a way that you can make the false discovery rate smaller below some sort of threshold? Again, I want to reiterate that such an approach has been developed specifically for studies where there's a very large number of tests, hundreds of thousands of tests. So high throughput types of experiments. And so to make this a bit more concrete, we'll go quickly through an example. We're doing this for 10 tests. Don't try this at home. Use it. There's a large number of tests, but just to make things concrete, we'll just do it on 10. So the procedure is just so. So let's say we have our 10 tests here. So in this case, m equals 10. So what we would first do is sort our p-values from smallest to largest and then rank them each. So the second column is our p-value. We see we start with our smallest one all the way down to our largest one, and we rank them from smallest to largest. Then our step 2 is to compute whatever that rank is divided by m. And remember, m is the number of tests multiplied by whatever your threshold is. For this example, we're going to use FDR at 0.05. So this third column is that intermediate calculation. And it's sort of, where we would expect it to be under the null. And then step 3 is to say, okay, compare your p-value to this intermediate calculation. And if you draw your threshold at the largest p-value, such that the p-value is less than that rank divided by m times threshold. So if we were to do this example and try to declare what would be statistically significance controlled at an FDR of less than 0.05, it would be those first two p-values. And so the largest one we have that satisfies our criterion here would be a p less than 0.00 or a p value of 0.008. So that's sort of step-by-step how you would do the FDR, but you would do it with a lot more tests. It's important to note that there's an FDR-based continuous measure of significance. Just like we were seeing before, you have your p-value, which is a continuum, and that's often compared to a pre-specified threshold. What FDR on its own that you want to cap that's itself a threshold, but there is a continuous measure as well, and that's called the Q-value. I'm not going to go into the weeds of how to calculate that, but just to define it, it's the minimum FDR that can be attained by declaring a certain p-value threshold to be significant. So just as an example of how you would define this, let's say we're doing a proteomics study, and it turns out that protein X has a Q-value of 0.021. So the way we would interpret that Q-value is to say, okay, 2.1% of proteins that have p-values less than or equal to protein X's p-value would be false positives. Or in other words, if we were to set our threshold at protein X's p-value, then that would be tantamount to controlling FDR at 0.021. And so you could do that for each of your proteins in this case. An important consideration here is that we need some user-specified tuning parameters to carry out this calculation, specifically a tuning parameter to estimate the proportion of truly null tests. Oftentimes the default in software is just to set it as the proportion of truly null tests equaling 1, but there are alternative methods. If this is something that's interesting to you, I recommend this story article in the proceedings in 2003. The appendix goes into great detail on how to do this. Other takeaways is that you're not controlling, well, what is the probability of the data given the null? What you're trying to control is something completely different. And you're trying to decide, well, which p-value to reject the null to achieve desired FDR. It makes explicit use of binary decision rules, so defining whether or not something is statistically significant. So it doesn't use that continuum at its core. You would need the Q-value to have a continuum. It does assume that all the null tests are independent. What's also notable is that unlike Bonferroni, which just depends on the number of tests you're performing, FDR calculations and Q-value calculations, they depend on the number of tests and the ranking of the p-values. So it depends on what else is in your p-value vector. We saw that the Q-value is an FDR-based measure of significance that can be on a continuum, but we want to be aware of how we're filtering before we carry out these calculations, because so much of it depends on looking at the distribution of the p-values that you have in your p-value vector. So if you start filtering out based on statistical significance, then you're skewing your distribution of p-values even before you carry out this calculation. So we don't want to filter based on association with the phenotype, because that can bias your findings. So here's some pro tips. So the pro tip is, if it's applicable to report a multiple comparisons correction, maybe you have a reviewer that just won't take no for an answer. The idea is to report both the raw and the corrected values. So we don't want to do the thing on the left where we're just reporting Q-values. And that's even beyond your philosophy about multiple comparisons. It's because it depends on these tuning parameters and filtering decisions. Instead, we want to have something more on the right where we have our raw p-values. And that way, any reader who maybe has their own philosophy about what should be done, they have the p-values and they can reproduce your findings, and they could also carry out their own calculations. The second one is make sure you understand the methods that you use. And if you're reviewing an article, make sure you understand the methods that you're reviewing. So for example, if you're writing an article, we don't want to do the thing on the left where we say after filtering using some sort of sparse regression procedure, which depends on the association between your metrics, we corrected for multiple comparisons using Q-values. We don't want to do that because that would skew our findings. What we would want to say is we filtered for overall abundance, and we report raw p-values along with Q-values. If you're not a statistician and you're reviewing an article, you don't want to be like the pit bull on the left who says the authors tested 4 candidate metabolites and raw p-values are meaningless without FDR. Instead, we want to know what it's fair to ask the question, but you kind of want to know your lane here. And so it's totally fair to say, hey, the authors tested these 4 candidate metabolites, a statistician should be consulted to determine whether multiple corrections is needed. Pro tip 3 is to understand that context matters. And so finding a result statistically significant at whatever threshold doesn't obligate your action. So this is not a question of what do I do or what do I believe. It's really just a question of what do the data say. And just to give you a toy example of how fraught this can be, we need to think about like, what is the cost of the action? What is the consequence? And bringing in some decision theory, what is the risk-benefit trade-off? And so let's say, for example, we have a clinical study where we're comparing a new treatment to a placebo for some rare fatal cancer. And we found that the new treatment is associated with a higher rate of remission than the placebo, with a raw p-value of 0.01, Bonferroni of 0.02. But let's say it also could have the effect of potentially accelerating death. So let's say it's also associated with a higher rate of death, uncorrected p-value of 0.03, Bonferroni corrected p-value of 0.06. So in this case, what do you do? In this case, the statistical significance is only really one part of the question. We have to think about, well, what are the costs and consequences in the context of our decisions as well. And that brings us back to that one article that we had where the nuance is looking at, well, what is the source of some of the debate and what are the real concerns here? And so the real concern is, what is the cost of making an error? So it's not just enough to say, well, when I Bonferroni corrected, the remission was significant, but the death was not, so I'm not going to worry about it. There's more to it than that. So some resources, I know some folks have asked about the slides. If you like to read, here's some of the articles, and including some of those front page titles that I showed earlier. And since you are sticking around to the end, we do have a bonus pro tip for you, which is, please, if you have no results, submit them for publication. And what I hope you're seeing here is that the debate about multiple comparisons is not necessarily about the math, but in some sense, it's kind of about the behavioral economics. It's about this trust and honesty issue, or the concerns about the honesty issue. In other words, distrust in the honesty of researchers. And this is more having to do with, well, what are the incentives of making these decisions and what are the beliefs about what's publishable? So why are researchers concerned, or why are reviewers concerned about researcher honesty and why they want to make their findings look more significant maybe than they actually are? Well, it's because of the thinking that, well, they need to have significant results to get their stuff published. Well, if you defang that incentive structure, maybe that becomes less of an issue and the debate becomes less fraught, and we're more willing to use the methods that match with our hypotheses, and that would be less of an issue. So if you're a reviewer, and those of you who are editors or future editors, if you see a well-motivated, high-quality, well-conducted Null study, be nice to it. And this is beyond just the multiple comparisons debate. This is more having to do with reproducibility and just using smart resource allocation. So from a selfish perspective, if I have a hypothesis and like 5 different research groups tested it out already and it didn't work, I would want to know about that before I waste my time and energy on it. Similarly, if I'm doing a meta-analysis, I want to make sure that the findings that I'm including in my meta-analysis or systematic review are actually reflective of the research that's being done and not just the result of publication bias. So if we can defang that incentive structure, maybe there is less of an incentive to game the metrics to give the results that we want. And then that will hopefully play a role in quelling this debate. So thank you so much. I know that that's an unpopular hot take, and XKCD, as much as I love them, they've made fun of it by saying, "Dear Nature magazine, I found no evidence sufficient to reject the null hypothesis in any research areas because I spent a whole week playing The Legend of Zelda, Breath of the Wild. I'll send you another update next week." And so the punchline here is that the push to publish negative results seems kind of weird, but I'm happy to go along with it. So we're not asking you to play video games instead of doing high quality studies. We're asking you to do high quality studies, and if the results happen to be negative, please submit them and please be a kind reviewer. So I'd like to thank the rest of the campus outreach committee and my funding as well. So with that, I'm happy to take any questions you may have.
And if anyone in the Zoom has questions, please put your hand up and we'll get to you. And if you don't have questions, there's a survey for our Zoom participants in the chat.
I like the idea of publishing about p-value and the p-value. I don't think that. What do you see most often? When we use literature, do you see FDR?
Yeah, so I see FDR as being the most common approach that's used to control for multiple comparisons. And it's for the rationale that was mentioned earlier. There's a concern that if you use Bonferroni or Bonferroni's cousins, that it ends up being too conservative. But if you do nothing, that's not going to be well received. So I think folks a lot tend to gravitate towards FDR because it tends to be seen as a middle ground. I think the context matters because what we're observing is that, again, it's not the math, there's a human element to this and tradition as well. And so the GWAS community, it's fairly standard for them to use their 5 times 10 to the negative 8. And so what they did is they did the do nothing approach. They just picked a very stringent alpha and didn't correct. In the microbiome, I see FDR used a lot. I could see in my work, I do tend to report both. If I'm doing something lower dimensional, I tend to just report the p-value, and I've been successful at pushing back at reviewers who ask for multiple comparisons. Oftentimes because the way they're asking about it tends to have a level of arbitrariness to it. Like, well, you should do multiple comparisons adjustment for this set of tests, but not this other set of tests. And it's like, you're literally just, explaining why people don't like this. And it's because it's arbitrary. What is your family of tests that you should include? And that could be seen as a tuning parameter that not everyone necessarily agrees with. So I had been able to push back on that, saying, look, I report all my p-values, the exact p-value. Anyone who wants a certain multiple comparisons adjustment, they have the results, they can carry it out. I think also on a pragmatic level, as mentioned before, having that comma separated value supplementary table is often helpful, sorted by p-value, because irrespective of whether you're doing a multiple comparisons adjustment or not, much of the results and the discussion is dedicated to whatever the top hits are. And so those usually end up reaching the threshold no matter what you do.
Yeah, no, I think there's another reason try something, ask a question. Did anyone else see this? And nobody saw it because they had to set their threshold at 0.000001, even though it was highly related in the previous study, but you can't see that if they don't do the supplemental period.
Right. Right. And another way of thinking is that your family of sequences or family of taxa that you're testing may be different from what someone else is doing. So if I'm looking at, like, let's say, I don't know, 500 proteins or 500 metabolites, and someone is just looking at one class of metabolites, if I do my adjustment based on that 500 and they just have their 10 or 15, they may be curious to see, well, I have this 1 or 2 metabolites, where did this land relative to this 500 metabolites? But my correction would have been too stringent for theirs because they're doing fewer tests. if you're, granting that any correction should be done at all.
I think what you're pointing out is that you get exactly the same results for particular level and get very different Q values based on whatever else they have to do it. Which is why I think the Q value brings into play essentially what.
Right. So and then again, this gets back to, what exactly is your hypothesis? Are you testing, is it a global hypothesis or is it, multiple hypotheses that you're actually testing? And that's something that tends to be not explicitly stated. It tends to be implicit. Any other questions? Going once. Going twice. All right, no sale. Thank you everyone for attending our first post-pandemic IGS Campus Outreach Committee seminar. Thank you. Oh gosh, I think we still have to figure out who's talking next and when that is. Okay, so it looks like it'll likely be in the fall. We know a lot of people go on vacation during the summer, so keep a lookout in your email in the fall.